And I've been involved in sustainable design for about 30 years. And fairly recently, I came to the conclusion that sustainability alone is not enough. We actually need to move on from sustainable design to a realm of regenerative design, which aims to optimize positives. And that's what I'm planning to talk about today. So, why do we need to do this? Well, this graph shows what we have to achieve if we're going to stay within what is regarded as a safe limit of no more than 1.5 degrees centigrade of warming. So that is the rate of reduction in greenhouse gas emissions that we need to achieve. So that's totally unprecedented in human history. And I think it's clear from that there's no way we're going to achieve it just by tightening up the knobs on the existing paradigms. We need to think in a whole new way. So let me explain what I mean about the shortcomings of sustainable design. So this diagram from an architect called Bill Reed of the Regenerative group shows different levels of achievement in environmental design. So the very lowest level is conventional practice, which you could characterize as one step better than breaking the law. Above that is the world of green design. So I'm sure you're all familiar with rating tools like LEED and BREEAM and so on. And then above that is sustainable design, which the architect Bill McDonough has characterized as 100% less bad. And that's the problem, as I see it, with sustainable design. The way it's framed implies that the best we can aspire to is to mitigate all negatives and to get to a kind of line of neutrality. The problem with that is that most of what we do is actually below that, is less than 100% sustainable. So it's just part of a degenerative system. And it's been quite painful for me to accept that a lot of what I've been working on for the last 30 years has really just been making things slightly less bad. And of course what we need to do is we need to get above this line into the realm of regenerative design, where we're striving to have a positive impact in everything we do. Just as people debated quite a lot 25 years ago, what's the ultimate in sustainable design? I think there's now a really interesting conversation to be had about what does regenerative design mean? What would the ultimate in regenerative design look like? And what I'm going to be arguing over the next 40 to 45 minutes is that one of the best sources of solutions in regenerative design is biologically inspired design approaches, particularly biomimicry and biophilia. So biomimicry, some of you may be familiar with this, the essence of it is it's about looking at how things have been solved in biology and learning from those solutions to develop innovations that suit human needs. So I'll give you a couple of examples of this so you're all familiar with what I'm talking about, and then I'm going to go on to talking about projects that use biomimicry in regenerative design. Some biomimicry innovations have quite amusing starting points. So this one is a true story. It starts with a marine biologist whose genuine name is Dr. Frank Fish. And he was looking at humpback whales one day, and he noticed that they have these lumps on their flippers. They're called tubercles. And he wondered what they were doing. And it turns out that these actually improve the hydrodynamic performance. So humpback whales swim in quite slow, tight circles when they're feeding. And these tubercles improve their performance at slow speed. So Dr. Fish thought, well, I know what I could do with that. And he developed a new wind turbine blade that has these lumps on the front edge. And it's claimed that these can produce as much as 5% more energy over the course of each year. Because normally what happens is when the wind speed drops to a low level, the turbines stop turning, and then the wind speed has to pick up quite a lot before they start turning again. So these maintain operation at slow speeds. This is one of my favorite examples of biomimicry. This is called the dog vomit slime mold. And slime molds are single-celled organisms which form minimum distance networks between sources of food. And in 2009, some scientists at Hokkaido University in Japan carried out an experiment with a map of the Tokyo region. So they put a little source of food, those are the white dots, on each of the cities surrounding Tokyo, and then they put a slime mold on Tokyo itself. So the slime mold spread out quite quickly, located all those sources of food, and started optimizing the connections between them. When it had finished, that layout exactly matched the railway network in that part of Japan. But it had taken the engineers thousands of hours to arrive at that optimization. But the slime mold did it in just 26 hours. So that shows what we could achieve if we could learn more from the way that biology has solved problems. Probably one of the oldest examples of biomimicry is shells. So birds, shells, and seashells. And we know from architectural writings that the architect for the cathedral in Florence, the Duomo, Filippo Brunelleschi, he looked at bird shells and seashells to help him design the thinnest and largest possible dome. What we have now is the huge advantage of superior scientific knowledge. So if you look at one of those shells, it's got an abalone, that previous slide. If you look at one of those under a powerful microscope, this is what you see. It's made up out of these layers of calcium carbonate, and those are connected together with a flexible protein. That gives it amazing resistance to crack propagation. So at a chemical level, that is almost 99% the same as ordinary blackboard chalk. But because of that microstructure, it achieves 3,000 times the strength. And my office used this example to develop a design for a house called the abalone house. And here we were learning from the abalone in two ways, partly from the overall folds and the shell structure, which gives it stiffness, and then also from the microstructure. So this is built up out of layers of tiles, and it would use about half the amount of material of a more conventional house. So you could characterize biomimicry by saying that it draws on the most amazing design sourcebook ever. A design sourcebook that has benefited from 3.8 billion years of research and development. So, of course, I'm referring to the long and ruthless process of evolution that has resulted in some pretty amazing solutions that we can learn from as designers. And in this talk, I'm going to, first of all, talk about regenerative landscapes, then talk about regenerative cities, buildings, and materials. So, starting with regenerative landscapes, there's a project that I've been working on for quite a long time now, over 10 years, called the Sahara Forest Project. And what we were trying to do here was to address multiple challenges simultaneously. So sometimes there's a tendency for architects and environmentalists to just focus on one problem at a time, whether that's, say, climate change or water shortages or biodiversity loss or whatever. And we thought that maybe with some clever integrated solutions, we could address multiple challenges simultaneously. And we were looking at some of the world's deserts, and we discovered that actually a lot of the world's deserts were vegetated a fairly short time ago. So for instance, when Julius Caesar arrived in North Africa, what he found was this wooded landscape of cedar trees and cypress trees, and his armies cut down those forests to create an intensive farm, which supplied the Roman Empire with about 500,000 tons of grain every year for a long time. But after about 200 years of that, they had substantially trashed that landscape. It was no longer anywhere near as fertile. It even changed the rainfall patterns. So we know from the historical writings of Pliny that used to be really quite a plentiful rainfall area with a lot of biodiversity in the forests. And what Julius Caesar's armies did was that they started a model of extractive land use, which continued for the next 2,000 years. So what we were trying to do was to look at ways of working on the edges of those deserts to perhaps push back the boundaries of the desert and also benefit from the incredible energy intensity that exists in hot, arid regions. if you look at the amount of energy that the Earth receives every year, we receive about 6,000 times as much energy from the sun as we currently use in energy from all forms. I'm not suggesting it's going to be easy to shift from the fossil fuel economy to a completely solar economy, but that statistic of 6,000 to 1 does at least suggest that it's possible. It's a challenge to our ingenuity. This was the first visualization we created for the Sahara Forest Project, and what we were trying to do here was to bring together three core technologies. Firstly, it's a greenhouse that is cooled and humidified with seawater, and it captures some of that fresh water in a process inspired by a fog-basking beetle that lives in Namibia. So that was one technology, the seawater-cooled greenhouse. The second one was forms of solar energy, such as concentrated solar power, and the third was desert revegetation technologies. And when you bring these three together, it turned out that they were much more effective and productive than they would be individually. So there were symbiotic relationships between these. And one of the most interesting ones was that the shade created by those mirrors makes it possible to grow a whole range of crops underneath that would not normally grow in desert regions. We built a version of this in 2012, so this was opened by the Emir of Qatar during the 2012 climate change talks. This was the project being built, and this was it on opening day. So we managed to grow cucumbers with half the amount of fresh water of conventional approaches throughout the summer with no active cooling. And alongside all the more technical aspects of the project that we were trying to refine, we also monitored what this was doing to the biodiversity. We had a hunch that this was going to be delivering some kind of regenerative benefits. So we made a note of any birds, mammals, and insects that appeared on site. And this infographic shows what we achieved. So this is set out according to taxonomic classifications. And the first things to appear were flies, so nothing particularly interesting there. But then, literally the same day that the first plants came to site, we had the first birds. And very soon after that, we had the first insects, grasshoppers, and then crickets. And about a month later, we had the first butterflies. Bear in mind that this was at least 5 kilometers from the nearest significant patch of planting. So it's quite amazing where all this stuff comes from. And then, as the plants got more established, we had other types of birds, like wagtails, and we were getting more insects. And then we had the first problematic species to deal with, that was rats, and their numbers were expanding rather rapidly, but never mind, we were still getting more birds and insects, which is nice. Then we had mice to deal with as well, which was slightly annoying, but anyway, more birds, more insects, which is very nice. And then, 3 days after the algae ponds were filled, we had the first dragonflies. And I don't know where they came from, because this was a long way from the nearest dragonfly habitat. But there they were, within 3 days of filling those algae ponds. And then we had a visit from a feral cat, which was quite convenient, because the number of rats and mice started going down, and we were still getting more birds and insects. And then we had a visit from quite a rare bird. It's called a hoopoe, not often seen in Qatar. The next one is a bird called a rufous-tailed shrike. And then we were getting other types of wagtail, more insects. And eventually we had the first indigenous mammal. This is called a jerboa. It's like a little hopping kangaroo. It leaves very distinctive tracks on the ground. That was all achieved in just 8 months on a site 100 meters by 100 meters. And I'm convinced that if we were to do that on a larger scale over a longer time period as well, that regenerative effect would be even more pronounced. So this is what biomimicry can do for arid landscapes, restoring areas of desert to higher levels of biodiversity, at the same time as generating all sorts of useful materials. So, moving on now to regenerative cities, what would it mean to apply biomimicry to urban design? The most persuasive model I've heard for how we should go about designing new cities or new bits of city comes from a group of consultants in the US. They're called Biomimicry 3.8, who I've worked with on a number of projects. What they argue is that when you're designing a new piece of city, what you should do is you should start by identifying how a pristine ecosystem in that part of the world would function. How much oxygen would it produce? How much carbon would it sequester? How much water would it filter? How much food would it produce? How much wildlife would it accommodate? And those should become the metrics for your new piece of city. We're nowhere near that at the moment, but I'm absolutely convinced that that is possible. And when we get to that point, then we could reasonably argue that we have integrated that bit of city into a long-term, stable and regenerative system. And although I wouldn't defend this building in terms of the amount of concrete it's used, I think it is an interesting example of what kind of architecture this could involve. So buildings that incorporate a lot of planting for the benefits that they offer in terms of modifying the microclimate, accommodating wildlife, even producing food. And I think one of the biggest differences we would see in a regenerative city would be in the spaces between buildings. This is a fantastic example of what was achieved in Seoul in South Korea. This river, believe it or not, used to be covered with a 10-lane motorway. And the mayor of the city persuaded people to tear that down and to restore this river and create this fantastic linear park. So this is now a way that people can walk and move around the city. And it's even reduced the temperatures in that part of the city by about 5 degrees centigrade. Another big thing that we'll see in regenerative cities is that they increasingly start to function like ecosystems. So you probably remember diagrams of food webs from your school biology lessons. Well, increasingly, that's the way we're going to need to see cities. So that they're analogous to an ecosystem of different organisms where the waste from one becomes the input for something else in that system. And it moves towards being a highly productive zero-waste system. This is a diagram for an extension to Stockholm. It's called Hammarby Sjöstad, where they did exactly that. They were trying to get every bit of waste to do something else. We pursued similar ideas on the Sahara Forest project. That was the previous project I showed you. So essentially what we had is a cluster of synergistic technologies here. So that's desalination, that's algae. These are plants called halophytes that can grow directly in seawater. This is concentrated solar power. These are the seawater-cooled greenhouses. These are the evaporator hedges, external crops, salt processing, and this is biochar. So that's a way of turning agricultural waste into almost pure carbon, which you can then put into the soil to sequester carbon in the soil. And in simple terms, we're using what we have a lot of, sunlight, seawater, and carbon dioxide, to produce more of what we need: biomass, oxygen, electricity, crops, and materials. And I don't have time to talk through all those interconnections, but we were deliberately modeling this on ecosystem models, where the waste from one part becomes the input for something else in that system. And when I show this kind of diagram, some people, they think, well, wow, that looks incredibly complicated. You sure you want to do that? Well, I believe this is the kind of complexity that we have to embrace if we're really to design proper regenerative cities. And it's actually nowhere near as complex as a real ecosystem. And with improvements in digital design tools, it shouldn't be that difficult to design this way. In fact, we developed a design tool that makes it easier to design these systems. So what this allows you to do is to input technologies with their resource flows and to connect them up. It shows here anything that is underutilized, and that's a sign that you could add something to the system to create more value, to transform waste into value. And then you can click on the play button and it shows you how it functions. It shows you anything that is not being used. It shows you, it also allows you to test for resilience. So you could cut any one of those links, and if that results in the whole system breaking down, then that's a sign that you need to add more buffering or duplication to make it a more resilient system. And steadily, that would move towards being a highly productive, zero-waste system that runs entirely on solar energy. Moving on now to regenerative buildings. This first project that I'm going to show you is called the Biomimetic Office. So this was an opportunity for us to apply biomimicry to a fairly conventional building type. And to do this, we got together a really fantastic team of consultants, so some of the best people I've got to know in my career as an architect. And we included in the design team a biologist who could help us identify solutions in biology to some of the challenges. In the first workshop, what we did is we tried to divide up the challenge of an office building into lots of distinct functional challenges, like how do you bring light in, how do you structure this, how do you make foundations, how do you ventilate, that kind of thing. And then we looked at how those kind of problems have been solved in biology. One of the key challenges we decided was how we would bring light into this building. We wanted to make this, as far as possible, naturally lit. And that was partly to save energy and partly because that's better for human health. And with our biologist, we looked at examples of how light is gathered and distributed in biology in interesting ways. This first one I'm drawing, this is the eye of a spookfish. So spookfish have these amazing structures in their eyes, these mirror structures which point downwards. And those mirrors are able to focus very low levels of light coming up from the ocean, so that's bioluminescence, and focusing it onto the retina. The next one we looked at is called the stone plant. So this is a plant that lives in deserts, and for reasons of thermal stabilization, most of the plant lives below the ground, and then the light comes down to the basement through a kind of roof light where the chemical reactions take place at a steady temperature. The next one is a starfish called a brittle star, and this has evolved a covering of near optically perfect lenses on its skin. And these are able to detect very small amounts of light and movement, so it can see predators before they see it. Now these three examples, and actually many others that we looked at, encouraged us to think much more creatively and deliberately about how we would bring light into this building. A fairly conventional way of designing for light in offices is to just think about the right distance between the window walls. In London, you can often find offices that are 25, 30, even 40 meters deep. And you know those are going to be high energy buildings because they'll be artificially lit and ventilated. So what's the right dimension? Well, we reckon it was about 12 meters. So no one is further than about 6 meters from the nearest window. And then thinking about what this implied in terms of the building form, one approach would be to just take these narrow floor plates and stack them up into a tower, which would be fine if we were working with a dense urban location. We wanted a concept that was more universal than that, so we looked at two other building forms. The first was a ring of office space around a central atrium, and then the next one was a more linear approach, where we have two linear blocks and a linear atrium down the middle. So it was that last one that seemed to work best when we analysed the light levels. And using daylight software, looking at the building in plan, what we found was that we were getting this curved pattern of shading because of the shading effect of the opposite block. The next design move was to simply bend those floor plates so we get a very even quality of light all the way along. That produced two further challenges. The first was that narrow floor plates aren't particularly good for creative clusters of people. You need some wider areas. And also this wasn't making very efficient use of a rectangular site. So then, learning ideas of surface area to volume optimization in biology, we elaborated this plan form into this undulating shape. So we still had no point that was further than 6 meters from the nearest window, but now we were getting better facilities for creative clusters of people, and we were making more efficient use of a rectangular site. Still looking at daylight, but now looking at the building in section, we found that it was reasonably easy to get enough light in the top parts of the building. The challenge was how to get the light further down to the lower floors. We looked at the possibility of harvesting light near the top and focusing it into fibre optic tubes. And for this we studied a rainforest plant called Anthurium warraquinum, which lives in very low light levels of the forest floor. And this plant has lenses on its leaves which somehow focus diffuse light. And the actual science of that was pretty complex, so there wasn't time to get into that detail during that project stage, but we're going to come back to that. What we did conclude was that there was a good case for incorporating a mirror, a pair of mirrors actually, inspired by the spookfish, that would bounce light into those lower floors. And then thinking about what we would do underneath that, we thought this was a great opportunity to design a meeting room with a really dramatic quality of space that would add value to the building, and it could be let out for functions. So now moving on to the structure, what we were trying to do here was to minimize the amount of material that we were going to use. And in biology, you can often find examples of structures that are really quite complex, and they achieve their amazing resource efficiency by putting the material exactly where it wants to be. So in this example, I'm drawing a section through a bird skull. And bird skulls are made of very thin layers of bone, which are connected together with struts and ties. So it's like a combination of dome technology and space frame technology. And this is what our biologist, his name's Professor Julian Vincent, this is what he said you find in biology, because in biology materials are expensive and shape is cheap. So you end up with complex shapes and a minimum of materials. And this is another example that we looked at. This is the bone in a cuttlefish, where you have very thin layers of bone, and this time they're connected together with these undulating walls. So again, it's a complex, very efficient structure. We then analysed a fairly generic column and floor slab arrangement. And we were looking at which bits of that structure were working hard and which bits were not really doing much. So all the bits that I'm shading in dark here, these are the bits that are not doing anything structurally. And if we were to do what biology does, then we would follow the shape that it wants to be. And you would end up probably with hollow columns, because the middle is not doing much. The floors would be deeper in the middle, and then you would take out the excess material with void formers. So this is actually only a fairly small departure from existing building technologies, and we were getting reasonably close to the examples that we'd identified at the beginning. So saving a huge amount of material, and we reckon that we could design this using about a half of the amount of concrete of conventional approaches. And then if I had more time, I'd love to tell you how we learned from curved shells and curved leaves to design a new glazing system which uses about half the amount of glass and a quarter of the amount of aluminium framing. And how we learned from folding beetle wings to design a shading system that lets in exactly the right amount of light and converts all surface light into electricity. This is how the building looked after we completed the commercial feasibility study, showing that we could design this for a sensible price. It would be slightly more expensive than a conventional building, but the market research we did showed that it would let out for about 25 to 30% more than a conventional building. So there was still a good business case for this. And this shows some of the ideas I was talking about, the form driven by daylight. That's the spookfish auditorium in the middle. And then you may just be able to see, this is the curved glazing here that uses very thin glass in a new way. And then this is a view of the atrium, and that's the spookfish auditorium. These are the mirrored surfaces that bounce light in and so on. So one of the engineers involved has predicted that if this gets built, it should be one of the lowest energy office buildings in the world. I think it would also be a much more enjoyable space to work in because of the quality of space and light. So another example of a regenerative building type that we've worked on is a zero-waste textiles factory. our client wanted a building that was going to be zero carbon, as close as possible to closed loop in water, and to be as close as possible to zero waste. And here, again, we looked at the characteristics of ecosystems to help us design this. So conventionally, human-made systems are simple and disconnected, whereas biological systems are complex and interconnected. Ours tend to be linear and wasteful, whereas biology works with closed loops and zero waste. Biology is adapted to constant change, doesn't use long-term toxins, runs entirely on current solar income, and is optimized as a whole system, and very importantly is regenerative rather than extractive. So how could we apply those ideas to a textile factory? Well, we conceived of this project as having three main realms. There's the water cycle, the energy cycle, and then the factory itself. And within the factory, you have a lot of different processes, each of which has its own resource flows. The big change came from changing the energy system from a fossil fuel system to one that's based on biomass, combined heat and power. So that would provide heat and power to the machinery in here, and we were able to recapture a lot of waste heat as part of this process. We were looking to reuse all the food waste to put into a biodigester that would produce gas to run one or two of these, and also produce compost. And then for the water cycle, the big breakthrough came from designing out all the toxins in the system, because that would allow us to use entirely biological forms of water treatment. And by doing that, we could get close to closed loop on water use. In the factory itself, we designed this so that it would be naturally lit, and it would have windows down the sides so people would get a view out to nature. And then this stuff down the middle, this is actually the biological water treatment. So it uses plants and microorganisms, and it's giving a double benefit. It's treating the water as well as giving something nice to look at from the windows down here. And then this is the staff canteen, so at least 3 times a day people can get a break from the working environment. And from the condition of the site at the start, which is really quite low in terms of its biodiversity, incorporating this kind of biological water treatment would substantially improve the number of birds and insects and plants on the site. One of my favorite examples of a regenerative building is this one in Singapore. This is a hospital. It's called the KTP Hospital. And this was designed specifically using biophilia. Biophilia is the theory that because humans evolved in direct contact with nature, there's a lot of evidence to suggest that we are happier, healthier, and more productive when we're in regular contact with nature. There was a previous academic study done on a hospital in Pittsburgh, and there was one particular hospital ward where all the patients were recovering from the same operation, so it was a good controlled experiment. Half the beds had a view to a building opposite with a blank brick wall, and the other half of the beds had a view to a planted courtyard. The patients in the beds with the view of nature, they recovered 8% more quickly and needed half the amount of pain-relieving drugs as the other patients. So that shows just how much biophilia can achieve, not just in terms of human benefits, but also in economic benefits. Imagine how much money you would save if all our hospitals treated people 8% more quickly. So that's what biophilia can foster in healthcare buildings. We ought to make this absolutely standard in all healthcare buildings and in other buildings as well. You know, why not design offices so they improve people's productivity? Why not design schools so that they improve people's concentration and learning outcomes? Why not design houses that are healthier and so on? So the final bit I'm going to talk about is regenerative materials. Now this image here, this is a marine organism called a coccolithophore. These are pretty remarkable things, really. They grow these absolutely beautiful structures out of calcium carbonate. And you find millions of these in a single cubic meter of seawater. And these organisms here, these were part of James Lovelock's Skya theory. I'm not sure if you've heard of this, but James Lovelock came up with this theory that the Earth actually operates very similarly to a self-regulating organism. So it's a complex of nested systems at various scales. And there's a lot of evidence to suggest that historically, levels of carbon dioxide in the atmosphere were regulated partly by these organisms. When carbon dioxide levels rose, you would have had massive blooms of these. Just trillions of these would be growing and falling to the ocean floor and building up layers of limestone, which would transfer carbon from the atmosphere into rocks and re-establishing the balance. So the lesson you could draw from that, if you're interested in biomimicry, is that one of the solutions to climate change, not the only one, but one of the solutions would be to grow more stuff, make more materials out of atmospheric carbon. So for instance, at the moment, concrete production results in about 8% of the total global greenhouse gas emissions. But if you look at the closest example in biology, that would be coral reefs. So those are large-scale mineral structures, and the contrast is profound. When we make concrete, it emits vast amounts of CO2, about a ton of CO2 for every ton of concrete. Coral reefs achieve the same result, but by taking carbon out of their environment and sequestering it into a product. This is an interesting example of a regenerative material. So this is called Biomason, and this technology allows you to put sand into a mold, and then you add a calcifying bacterium and a certain amount of nutrient solution, and in just 3 to 5 days, that bacterium turns that into a solid block, which is strong enough to build with. So normal bricks need to be fired at about 1,200 degrees centigrade. This all happens at room temperature, so no carbon emissions at all. This is a table that my company designed for an exhibition. So this was partly inspired by bone and tree growth patterns, and partly by the ribs of an Amazon water lily. So the structure is inspired by biology, and also it uses a biologically derived raw material. So again, taking carbon out of the atmosphere to produce a very efficient structure. And that's what we need to do more of. We need to find ways of learning from biology to produce incredibly efficient structures with biologically derived carbon materials. And to conclude now, I just want to say a few words about this amazing organism. So this is called a glass sponge, and this lives in quite deep ocean water, and these amazing lattice structures are being studied by structural engineers and trying to understand how they are so efficient. And the material itself, these fibers here, this is what the structure is made of, and those fibers go down into the seabed, and each of those is a glass fiber with higher optical quality than human-made glass fibers. And where they terminate, you have this cluster of lenses which are able to focus light from bioluminescent bacteria in the seabed, and that light gets conducted up these fiber optic tubes to put on a kind of lighting display that draws food to the organism. So that glass is made just with locally available materials of silica and carbon and a certain amount of other things at ambient temperature and pressure. And if you contrast that with the way that we make glass, we have to put a huge amount of energy into extracting stuff out of the ground, more energy in heating it up and processing it. This organism produces glass with probably 1/1,000,000th of the amount of energy of conventional approaches. And it demonstrates some of the things that we could learn from biology. So producing beautiful structures, finding ways of ultra-low energy manufacturing of materials, fostering symbiotic relationships. And if you remember at the beginning, I talked about biomimicry as a discipline that learns from 3.8 billion years of research and development. That's what we see here. 3.8 billion years of brilliant solutions, illuminated by previously unparalleled scientific knowledge, facilitated by previously unimaginable digital design tools. We've never had such an opportunity to rethink and design solutions fit for the next billion years. And this points to a completely new relationship with the living world. If we carry on with a metaphor of nature as something to be conquered or plundered, then we're in really deep trouble as a species. But this, biomimicry, points to a new way of seeing nature, as seeing it as not just a source of wonder, but as a source of some of the best solutions to help us design solutions, to help us design innovations that are much better for our buildings, that use less energy, and create a much better living environment. Thank you.